Good afternoon, sir. My name is Tan AIT2209555 from Group 9. Our group member consists of Goh Yanzhe, Lim Sui Long, Zhou Zikang, and Wang Yuxuan. The topic that we choose for the assignment is Robotics of Operating System-Based Reinforcement Learning in Robotics. So, without further delay, let's move on to the background of the articles. So, what is reinforcement learning? Reinforcement learning is a branch of machine learning where robots learn how to behave by interacting with their environments. The robot's cores and engines tries different actions and receives feedbacks in the form of rewards or penalties. Over time, it learns which actions produce the best long-term results. Here are the few tasks of reinforcement learning in robotics. The first one is autonomous navigation, second, motivation control, third, obstacle avoidance, and the fourth one is objects manipulations. Unlike traditional programming, reinforcement learning allows robots to adapt to dynamics, real-world environments without needing explicit instructions. Here are some popular reinforcement learning algorithms in robotics. There are Q-learnings, policy gradient methods, proximal policy optimizers, deep skill networks, actor critics methods like AIT306 and SAC. These algorithms help robots make smart decisions even in uncertain or changing environments. So what is ROS? ROS is Robots Operating Systems, in a middleware framework that connects different parts of robots like sensor, motors, and cameras so they can work together efficiently. It provides libraries, tools, and drivers for building, simulating, and controlling robots in real time. The key feature of the ROS includes modular architecture for easy system integrations, real-time data exchange between components, simulations, tools like Gizmo for visual trainings. Supports for many platforms include drones, mobile robots, and robotics arm. ROS is essentially for building scalable, flexible, and reusable robot systems. So, when robots is combined with reinforcement learning, the result is a powerful framework where robots can both learn and act. ROS handles the hardware and communication layer while RLs handles integrate intelligence decision making. These integrations allow researchers to train robots in simulations, then transfer the learned behavior to real-world systems, we commonly call as sim-to-real transfer. Together, ROS and IL are driving a development of more autonomous, intelligent, and adaptable robots. In my opinion, reinforcement learning is a smart way for robots to learn from experience instead of following fixed rules. The robot improves by trying things out and learning what works best. It's a powerful method because it helps robots adapt to real-world situations on their own. That's all for my part. Now I will pass the mic to Yanzhe. He will talk about motivations.
Now let's talk about the motivation. Why combine ROS with RL? Firstly, we have reliable communication and adaptive intelligence. ROS is able to deliver a modular framework for messaging between sensors, controllers, actuators, and more. RL brings trial and error learning to this structure, automating behaviors that were once hand-coded, which can vastly improve autonomy of robots. Modularity, scalability, and reusability. Using ROS lets us transfer policies across different robots and environments. By integrating RL, developers can rapidly prototype in simulation and seamlessly redeploy on real hardware with minimal rewrites in between. Next, we have efficient sim-to-real transfer. By leveraging ROS-compatible simulators like Gazebo or VREP, policies can be safely trained offline, which reduce hardware wear, lowering costs, and accelerating real-world deployment. Enhance autonomy in dynamic contexts. Real-world applications such as ABB robotic arms, UAV landings, and multiple robot coordination all benefit from learned behaviors that adapt to dynamic, changing environments, which can boost reliability and reduce human intervention. And most importantly, this review also aims to meet a critical need in cataloging recent RS RL works involving surveying algorithms, platforms, repositories, and guiding future research to fill research gaps. However, integrating RS and RL also comes with hurdles. Firstly, Noisy sensors and modeling errors. Real-world observations are often imperfect. Sensor drift, noise, and calibration issues often complicate and disrupt the learning perception process of robots. Second, we have dynamic environments. Moving obstacles and fluctuating conditions in real scenarios often require policies that can generalize well across contrasting scenarios, which can be difficult to implement. Next up, onboard computation limits. Embedded hardwares often lack the power for intensive RL models, requiring linear architectures or computation offloading. And complex ROS RL integration. In many of these type of systems, coordinating message passing, synchronization, and to achieve realistic physics is often quite complicated, especially when trying to bring simulation to a reality. Lastly, generalization gap. Training and simulation is not enough. Policies can very often fail in real environments unless robustness to visual and dynamic variation is built into the systems. So in summary, combining ROS and RL leverages modular communication and learned autonomy for more robust robotics. However, real-world deployment demands innovations in sensor handling, computation, integration, and sim-to-real generalization. So it is important for researchers to understand these dynamics between these difficulties, challenges, so that they can lay the groundwork for smarter, more adaptive robots.
Hello, my name is Wang Yuxuan. Now I want to introduce notable works using of policy, which is also the application progress of the current mentioned technology in robot obstacle avoidance, control, navigation, and path planning, and so on. The whole content can be summarized into 4 parts. The first part is motion planning and collision avoidance. The research first focuses on how robots can avoid obstacles safely and effectively in the multi-agent environment. For example, combines LSTM networks with reinforcement learning algorithms to break through the bottleneck of traditional behavior prediction. These methods not only perform well in simulation but are also successfully deployed on a robot platform in reality. The second part is robots manipulation and control learning. At the task level, the research covers typical manipulation tasks such as pick and place by introducing algorithms such as DQN and SAC. The robots can autonomously determine the grasping point or cutting path based on visual or sensor information. In addition, dual simulation systems collaborate to train models, achieving smooth migration from virtual to reality. This type of control strategy greatly improves the robot's ability to operate in uncertain environments and reduces dependence on maturely preset rules. Next part is autonomous UAV navigation and landing, using DTPG, SAC, DPC, and other algorithms to achieve autonomous and safe landing of UAV on dynamic platforms on unknown areas. Integrate the PS4 flight control system and a great ball simulator to achieve a complete simulation deployment closed loop. The last part is navigation. First is autonomous navigation systems. Adopt RL and SLM fusion methods such as DTPG plus SLM or SAC plus perception fusion to achieve autonomous navigation without preset maps. The system's design adopts a strategy combining global planning plus local learning, taking into account the global relationalities and local dynamic response. Second is path planning strategy and optimization. Adopt DQN, Q-learning, and other algorithms. Adopt DQN, Q-learning, and optimize the path strategies through PPR and DWA dynamic windows methods. At the same time, the introduction of green map, Q values, dynamic adjust, and other means excellent performance in multi-touch, multi-obstacle, multi-person, and multi-machine collaboration. These methods significantly improve the path efficiently, obstacle avoidance ability, and the stability of robots in complex and unknown environment. That's all for my part. Thank you so much.
Alright, I'm Lim. The review of my parts are benchmarking, safety control, localizations, and path planning. In benchmarking, are talking about communication between OpenAI gyms and simulation platform. The system optionally interfaces with autopilot software. Furthermore, safety framework ensure adaptive, data-driven, low interference learning with real-time validations and robust and uncertainty modeling. Then we have localization and path planning. It's talk about GPS, LiDAR, and GLONASS. The left down diagram highlights the processing step before sent to the command filter. Besides, ROS was used to manage communications between the path planning algorithm and the robot physical hardware.
Hello everyone, my name is Zhou Zikang. Next, please let me present you an overview of reinforcement learning in robotics. Let's look at the reinforcement learning process. Reinforcement learning involves an agent interacting with an environment to achieve a specific goal. This process is cyclical and involves several key components. The first is observation. The agent perceives the current state of its environment. The second is action selection. Based on a learned policy, the agent chooses an action. The third is reward. The environment provides feedback in the form of a reward, indicating the desirability of the chosen action. The third is policy adjustment. The agent adjusts its policy to maximize future cumulative rewards. Now let's focus on the fundamental principles of reinforcement learning. The Bellman equations is the groundwork for reinforcement learning algorithms, revolutionizing decision-making under uncertainty. The value of state represents the expected cumulative reward from a given state. The quality of the state it represents the expected cumulative reward for taking an action in a state. The Markov decision process is the systematic approach for decision making under uncertainty, which the policy is based on the current state only, and it integrates incentives, policies, and discount factors. Now let's talk about the categorization of RL models. The first is model-free RL. It learns the optimal policy directly from perception data. There is no environment model, which means it does not rely on a trained model of the environment. It is simpler and robust to environmental complexities, which why it is common in robotics. And the third is model-based RL, which learns the optimal policy by an explicit model of environment, which have improved behavior predictions, higher sample efficiency. But there is challenges for robotics. It is difficult because it is difficult to learn accurate environment models. And there is hybrid models which combines the advantage of both model-free and model-based RL, which have efficient data management and enhanced robustness against errors.
Now let's focus on some popular Model 3 RL algorithms. The first is deep Q networks. It enhances Q-learning with Q-deep learning for high-dimensional state spaces. It utilizes experience replay for offline learning. There's a variance of it, like double DQN and dual DQN. The second is policy gradient algorithms, which directly optimize policies by maximizing expected returns. It is suitable for continuous action spaces in robotics, such as reinforce and PPO. The third is actor-critic algorithms. It combines value-based and policy-based methods, such as A2C, A3C, and soft actor critic. The third is deep deterministic policy gradient, which integrates PG methods with Q functions. It is designed for continuous action spaces.
So our presentation conclusion in this paper is reviews combining RLS and reinforcement learning for robotics. It provides a comparative analysis, best practice recommendations, and suggests future works like improving sim to real transfer. So this all our review. Thank you.